So we will look at important PDF models, right. So this is obviously much nicer territory for all of us, right. We are not going to talk in abstract terms, we are going to talk only in very concrete, right, examples. So we can always talk of, right, omega equal to r, x of omega equal to omega, bing, boom, we have a PDF, right. I mean we have a situation where we can do this. So we will look at, I will do some numbering, the uniform PDF, right, on some closed interval AB. Actually it does not matter if the interval is closed or open, right, we will just assume closed, okay, but it is the same, there is no difference whether you include or exclude A or B, right. So what is this uniform PDF? Again since I do not need a random variable, so I am not going to put subscripts, right. Only if I define an x do I need to put fx. What is f of x is 1 by b minus a for a less than x less than b. As I said, it because of the nature of right of intervals and so on, it does not matter whether you include or exclude, but for the sake of completeness I am taking it like this, that is all, right. So this is one of the most important continuous situations that you see in practice, as we have already seen this in the spinning pointer case, right. More importantly, the 0 1, that is even more in a sense more basic than 0 to 2 pi, because that is the basis of all continuous random number simulation that you do, right, with the computer. Every software package will definitely, whether it is of the type of Python, every scientific computing package always includes a random number generator in 0 1, right. So we will write we need some notation like, for example, we wrote binomial, Poisson and all that. So uniform is a little on the big side, so we on the big, so it's the uniform is often written as UAB, right, with some script U. Instead of writing uniform, right, it is abbreviated to U. So, and of course by domain extension, which I forgot to say, I have to say that. So this is the domain extension here. So A and B can be any two real numbers, remember, right, A can be -1 and B can be 10, that makes no difference. The only thing you want is you cannot allow either A or B to become infinitely large, then of course this reciprocal does not make any sense, right. So the idea is that you take any two finite numbers A and B and you can define a uniform PDF in that over that interval between them. Okay. So this is a very, let me say, it is a very important model, because it says that what is the most important thing, the probability depends only on the width of the interval and not where it is. Okay. Now to go to some non-uniform models, right, all the other models of course are going to be non-uniform. The next one we will just list is this exponential PDF, right. This again is very important because a lot of lifetimes and so on are observed to follow this model. So here there is a single parameter here, lambda, non-negative parameter, lambda, right. So note that both of these f of x's, both of these PDFs have, this has a jump, right, at A and B, this has a jump at 0. So if x, that means x less than 0 here. Here of course it means x less than A or x greater than B, that is more very convenient to write it like this rather than, okay. So this, okay, if you think of this is going to be A, B like this is going to be, this is 0. So this random any random variable with this PDF clearly has 0 probability of being of taking on any values in a negative interval, right. So So along with the CDF, the PDF, you can also write the CDF, right. The CDF is always going to, in this case, be a what? Be a ramp between A and B. And here what is it going to be? If this is the discharging of a capacitor, the CDF will be a charging of a capacitor, right. So this gives for 2, I will just write only for 2, the f of x is what? 1 minus e power lambda x for x greater than 0 and is 0 for x less than 0. I am writing it, let me write it explicitly like this. Please check that, right, this must be the derivative of this for x greater than 0. Isn't it? Okay. So this is a single sided exponential. You can obviously also talk about two sided exponential. This also is right, is encountered in practice, right. Sometimes it is called Laplacian. Here, okay. If I write the C lambda mod x, right, where x is any real number. So this is now defined over the entire, the PDF itself is has non-zero values over the entire, right, real line, only asymptotically it decays to 0. So what would be the value of C? This is a standard question, right. You have to find the value of C by integrating this and setting it equal to unity. So you can clearly or easily, I hope, verify that C must be lambda by, right. So basically this lambda here, right, it becomes lambda by 2 when you consider the same type of function over the whole real line. So the the PDF looks like this. Remember the e power minus lambda mod x. Right, now we will encounter many complicated arguments for the exponential function. So if once we get a more complicated argument than just simply lambda x or lambda mod x, we will use exp. So I hope that is okay with everybody here, right. Just to do the formatting on the same line, right, we do not want to start a superscript which is all squishy, and especially in LaTeX, right, please use backslash exp, right, to typeset that this portion. Here it is okay, but as we will see when we look at Gaussian and so on. Okay, let me look at Gaussian next, the very important one, right. So I have to do this for a Gaussian piece. The famous sign that we use to tell, right. This is very important, right. We can do here. This is also extremely important, right. So here our f of x is going to be what? What does anyone remember? So you have x per, first of all you have this. What do you have? Minus x minus m, some number m by 2 sigma squared. We will use the standard notation. What is the constant? Or we will think of it like this. What values of x? All real, right. So this, right, is such an important PDF because of the way in which it appears in such a variety of applications. That again so for Laplacian or the exponential Laplacian, we are not giving it a name. This is going to be called the normal Gaussian or normal, and you say that a random variable with this PDF is written n m comma sigma squared, right. So, the value of sigma squared, or if you want you can think of this as somebody said as root 2 pi sigma squared. So, this value of sigma squared you give as a parameter here. So, obviously that sigma squared is a positive parameter. M can be any real number. There is no restriction on M. Turns out that M is a point of symmetry of this PDF. So, we have to look at what it looks like. We have to see, right. So, for what does it look like? The famous bell-shaped curve. I can't do justice to it. This is the best I can draw. I think this is okay. Luckily, we don't do too much of this in this course. So occasionally, we draw pictures. This point of symmetry is M. So 0 can be anywhere. It doesn't matter, right? This can be 0 here. So the point of symmetry can therefore occur at any point on the real axis, right? Can be negative or positive. There is no restriction on that. But what about sigma? What is the role of sigma in this? That's English. If I fluctuates about its mean. I am interested in small, as usual, like in the Poisson case, right? We want to vary sigma from small to large, right? So what is it going to look like for small sigma, and what is it going to look like for large sigma? For small sigma, you get a nice high, sharp high curve concentration around M. Remember. So, this is what you get for small sigma. So, as sigma increases, the spread increases, always remember this, right. Sigma or sigma squared does not matter, it is preferable to look at sigma squared. Okay, the sigma does not matter really, right. Since I have written it as m comma sigma squared, I am focusing more on sigma squared, right, than sigma itself, but it's right, sigma is obviously the positive square root of sigma squared, so the two are basically inseparable. So as you increase the sigma squared, you spread out. The distribution has heavier tails for larger sigma. Similarly, the exponential which I erased here, for large lambda it is concentrated around 0. For smaller lambda the decay is smaller. I have erased it here, but go back to your notes and make that point, right. The same kind of, for every PDF which depends on parameters, you should understand the effect of those parameters on the shape of the PDF. Right. So, in the limit it turns out that you get a degenerate situation as sigma goes to 0. Similarly, in the exponential case, right, you get a degenerate situation as lambda goes to infinity, it becomes very large, right. In other words, the e power minus lambda x, which is visible to me here, collapses almost to the single point x equal to 0. Similarly, as sigma goes to 0 here, this distribution collapses to the point m. So you get a degenerate case where all the probability is concentrated in a small interval around m for very small sigma. So you get heavier tails, right. The use of this word heavy tail is this comes up a lot, right. Okay, I will just leave it as sigma. Okay, so I think I will close here.